In this DeBacco University video, I'm going to go over how you determine the molecular geometry with more than one central atom in the molecule you're looking at. All right, looking here, we can kind of see the model we're going to be working with. Realize this represents the exact same thing, but it might show a little more of that three-dimensional shape, which is how we have to think about these molecules behaving. Now, when you have more than one central atom, you want to treat each central atom individually using the VSEPR theory, and then combine the local geometries to understand the overall shape of the bigger molecule. So all hydrogen atoms form a duplet here, hence they are stable. You can see here when we're talking about bonding, oxygen atom forms an octet, hence it's also stable. So again, we're looking here at these molecules also maintaining a high degree of stability, which is the reason why they're going through these bonds here. So just a general step-by-step approach: draw the full Lewis structure, identify all the atoms and bonds, highlight each central atom, usually atoms bonded to more than one other atom. Then you want to analyze each central atom separately, count electron groups, bonds, and lone pairs, use the VSEPR theory to determine the geometry around each atom. Determine local geometries, apply the VSEPR to each central atom. So for example, here with ethanol, CH₃CH₂OH. The first carbon in CH3 is tetrahedral. CH2, the second carbon, is tetrahedral. And oxygen and hydrogen have a bent shape. Combine the local geometries then. Visualize how each part is going to connect, and the overall molecular shape is a combination of those geometries, often forming either a chain or a ring or some other three-dimensional shape. Because we want to consider that three-dimensional orientation. Bond angles and lone pairs will affect this, and how the segments may twist or bend. Don't think them always on the same plane. There might be twists or bends, some that are closer or further away. So for example, butane, C4H10, each carbon is tetrahedral, but the molecule adopts a zigzag shape due to the bond angles. Now an example here would be CH₃OH, methanol. The carbon has 4 electron groups, tetrahedral. Oxygen has 2 bonding pairs plus 2 lone pairs, so therefore that would be bent. The overall shape is a tetrahedral carbon bonded to a bent OH group. And this tries to show that the overall molecular geometry is basically a mosaic of all the individual geometries there. Each central atom has its own shape, and how they connect defines essentially that full structure. So tetrahedral shape with respect to the carbon atom, a bent shape with respect to the oxygen atom. So we got these multiple geometries all coming together when you have these molecules with multiple central atoms.